Just let me know if you're able to see my screen.
Yes, sir.
Yes, sir.
Okay. Okay. So we had stopped at ML inequality, I guess, last time. We'll take the discussion forward from here, ML inequality. Okay, so it provides an upper limit on the absolute value of the complex line integral. Okay, so now before we go to the Cauchy's integral theorem, we need to talk about the kinds of paths and about the connectedness of a domain when you're talking about when you're doing complex integration. So these are we are interested in simple closed paths. Okay, simple closed paths. So simple closed paths are those paths which do not intersect and which do not touch themselves. Okay, so these are known as simple closed paths. So this is an example of a simple closed path. As you can see here, the path, it does not intersect itself, nor does it touch itself again. Then this is an example of a simple closed path. Okay, here this is not a simple closed path because the path let's say starts from here and it again intersects itself at this point. Okay, so it intersects itself at this point. So this is not a simple closed path. Again, this part, it touches itself at this point and at this point. So this part is also not a simple closed path. So you could have a complicated path that looks something like this. So this is an example of simple path and it's a closed path, and this is not an example of a simple closed path. Okay, so we are going to consider paths which look like this, either this or this, which are known as simple closed path. Can you just give me a second? I seem to be getting a phone call. Hello. Ah. My servicing or this look. Servicing. Jalukbari. জালুকবাৰী এই প্ৰাগজ্যোতিষ নগৰ তাতে এই হাইৱেটো যে আছে ৰেলৱে ব্ৰিজটো যে আছে যে তাৰে চাইডেৰে ৰাস্তা এটা সোমাই যায় যে সিফালে আছে নহয় মই তেতিয়া সেইখিনি মই মোৰ সেইটো পাৰ্মানেণ্ট এড্ৰেছ হয় কিন্তু মই হেৰি ইনষ্টলেশ্যন তাতে জালুকবাৰীত কৰাইছিলোঁ যোৱা বছৰ নহ'ব ঠিক আছে যোনে মানে সেই জালুকবাৰীত মানে হেৰি ইফালে সেইটো এৰিয়া চাই তাক এছাইন কৰি দিলে হ'ল কথা নাই নহয় কেতিয়াবা বজাত যাওঁ মোক টাইমটো কোৱাচোন কাৰণ ৰাইট মই এটা মিটিং এটাত আছোঁ তো 5টামান বজাত নহয় মানে সেই এনেই তোমাৰ কেইটামান বজালৈকে তুমি থাকা সেইবিলাক কাম কৰা কেইটা বজালৈকে মানে কেইটামান বজালৈকে আচ্ছা ঠিক আছে হ'ব দে তেনেহ'লে মই তোমাৰ এইটো নাম্বাৰত মই আৰু এটা নাম্বাৰত মই SMS কৰি দিম সেইটো নাম্বাৰত কল কৰি ল'বা হা তো তুমি ঠিক আছে 5টামান বজাত যাবা তেনেহ'লে 4টা 5টামান বজাত তেতিয়া যোৱা যাবা ঘৰত আছে মানুহ আছে দিয়া এবছৰ হৈ গৈছে ৱাৰেণ্টি নাই ৱাৰেণ্টি মানে এবছৰ মানে যোৱা বছৰ মই জুনত লৈছিলোঁ এতিয়া ৱাৰেণ্টি নাই দি দিম মই মোক কৈছে কথাটো হ'ব উম, উম, উম।
Sir, we can't hear you, sir.
Sir, you muted this call.
Unmuted myself. Sorry, so sorry. Okay, I thought I had unmuted myself, but I forgot to click on that. Okay, so let me again go back here. Okay, so let me again just go back to this. I'll start again. So sorry about that. Okay. So we talked about simple closed path, right? We talked about simple closed path. Now, a simply connected domain. So what's a simply connected domain? Okay. As per the definition which is given over here, a simply connected domain. What is a domain? Domain is a set of points. Okay. So domain, when I say domain, it means domain is a set of points. Okay, a set of points. So here, when we say domain, we are talking about the shaded region. Okay, so here the shaded region. Here the shaded region, that's the domain. Okay, so a domain in which every simple closed path encloses only points of D. Okay, that kind of a domain is known as a simply connected domain. Okay, so in other words, what we mean by that is this. Okay, what this means is the domain does not contain any holes. Okay, any holes. So you can see here, in this case, this dotted line that we have here, this dotted line represents, this is the boundary of the domain. Okay, this dotted line represents the boundary of the domain, and then this shaded region represents all the points which belong to this domain. And as you can see here, all the points which lie inside this simply connected path, all of them, they belong to the domain. Okay, so this is a simply connected domain. Okay, this is a simply connected domain. Next, here also you look at the boundary. The boundary seems to be a very complicated boundary, but if you look at it carefully, this boundary is it is an example of a simple closed path. The boundary here, in this case, the boundary is a simple closed path. And as before, the shaded region, okay, that contains the points in this domain, we find that all the points which lie inside this simple closed path, all of them, they are a part of the domain of this particular domain. Okay, so in this case also, the path, it contains only the points which belong to this domain. So this is also a simply connected domain. But here you see, that's the reason why I said, the domain, it should not contain any holes. Now you consider this, the outer boundary. Okay, let's say this is the boundary of this domain. Okay, now come apply this statement, if this statement is applicable here or not. The domain D is such that every simple closed path in D encloses only points of D. So let's say I take the boundary. This is a simple closed path. Does this simple closed path, does it contain only points of D? Of course not, because you see, this points of D are those which lie in the shaded region. What about points over here in this region? These points, they do not belong to D. Okay, only these points which lie in the shaded region, only they belong to D. So these points that I have written over here, these points, let me put them in some other color. These points, they don't belong to D. So it means there is at least one boundary which is a simple closed path, and that boundary contains points. These red points are those points which do not lie inside this D. So this is not a simple connected domain. Okay, this is not a simply connected domain. This is not simply connected. In a similar way, this is also not simply connected, because you can see here, you can see here that here, at least if you look at the boundary here, that's a simple closed path, but it contains some gaps. So it means these are the points, these are some points which, even though they lie inside the simple closed path, but they are not part of D. So it means this is also not simply connected. So these kind of domain, they're known as doubly connected domain. This is known as a doubly connected domain. Okay, this is known as a doubly connected domain, and this is known as a triply connected domain. Okay, so how many the connectedness that you can just visually you can inspect the domain, and you can find out what kind of connectedness does the domain have just by looking at the number of holes. If there is only one hole, if there is one hole, then it's a doubly connected domain. If there are two holes, it's a triply connected domain. Okay, so in general, if there are n holes, it will be n plus one fold connectedness. Okay, here how many holes are there inside this domain? Zero holes, zero number of holes. So it is simply connected domain, or one fold connectedness. Okay, this is one more way of looking at it. Simply connected means one fold connection. Okay, here also this also means one fold connect. Doubly connected means two-fold. Formally, this is what we call as two-fold connectedness. Okay, and triply connected means three-fold connectedness. Okay, so in general, if you have n number of holes, okay, if you have n number of holes, p minus one number of holes, and we call it as p fold connected. So a bounded domain whose boundary consists of p connected close connected sets without common points. So another way to check what fold connectedness is, just look at how many boundaries does it have. This domain, how many boundaries does it have? It has got only one boundary. This one also, it has got this domain, it also has got one boundary. But this domain, it has got two boundaries. One is the outer boundary, another one is the inner boundary. So number of boundaries in this case is 2. So it's two-fold connectedness. Here the number of boundaries is 3. So 1, 2, and 3. So 3 boundaries. So this is a three-fold connectedness. So you could have something like this. Okay. So I could have, this is one boundary, this is one, this is one, this is one, and this is one. So this is how many boundaries? 1, 2, 3, 4, 5. This is 5-fold connectedness. Okay, so that's how you can find out what kind of what fold connectedness does this domain have. Okay, just look at the number of holes or look at the number of boundaries that it has. Is this clear to everyone?
Yes, sir.
Okay, so let me just copy this here. All right. So that's about paths and connectedness. Okay, right. This is the same thing. Okay, D has p minus 1 holes. If there are p connected closed sets, it has got p minus 1 holes. So that's a p fold connected. Okay. Then this brings us to the Cauchy's integral theorem. Very important theorem, which will further lead us to something known as the Cauchy integral formula. So now let's say I have a function. Okay, I have a complex function f of z, and this complex function f of z, it is analytic. Okay, this complex function f of z, it is analytic, and you know what is analytic, right? We already know the definition of analytic in a simply connected domain. So what do you understand by simply connected domain? That domain does not have any holes. Okay, that's another way to look at it. So this example that we have here, we have a domain here. This domain, is it simply connected? Yes, it is, because it has got only one boundary, one fold connectedness. One fold connectedness means simply connected. There are no holes. Okay, so now suppose I draw a simple closed path. Okay, I draw a simple closed path which lies completely inside this D. This is an example. C is a simple closed path which lies inside D. Okay, C is a simple closed path. Okay, it's a simple closed path, and this simple closed path, it lies completely inside this D. So what the Cauchy integral theorem, what it says is, if I have an if I have a domain D, okay, if I have a domain D, and this function f of z is analytic, function f of z is analytic on this domain D. Okay, function analytic is, and function f of z is analytic at all points on this domain D. Then if I draw some curve, if I draw some curve C, which lies completely inside this D, then the line integral of the function over this closed curve, that line integral will always be 0. Okay, so that's what the Cauchy's integral theorem, that's what it says. Okay, so we can prove that So I'll just tell you one more thing. So it really does not matter which C. So this is one curve C. So now likewise, suppose I draw another curve, another simple closed curve. This is, let's say I draw another simple closed curve like this. This curve I call it as C1. According to Cauchy integral theorem, this C1, it lies completely inside D, right? C1, it lies completely inside D, and the function f is analytic on D. So that means if I ask you to find out the closed loop integral of the same function, okay, if I ask you to find out the closed loop integral of the very same function over this new curve, that also will be 0. Okay, now suppose I take another path, suppose one new path. Okay, so one new path which looks like this, let's say a new path like this. Okay, this path I call it as C2. Now is the same thing applicable here also? Can we say that the closed loop integral over C2 f of z dz, is this also equal to 0? What do you think? Any of you can respond. What do you think? This next path C2, can we say that this is true? This statement is true?
Not true, sir.
Not true. I mean, we should not say not true. We should not necessarily. Okay, not necessarily 0. It may be 0, but we don't know about it. We are not sure of this. Okay, this is not necessarily. This is not necessarily. Reason is we know that this is analytic over D, but we are not sure about whether it's analytic outside D. Maybe it could be. It is possible that this function could be analytic in this part. So in that case, this will definitely be 0. Okay, but we are not sure of that because we don't know about the analyticity of the function outside in this region. We are 100% sure that the function is analytic in this region. So any curve inside this region, which is simply connected, I could always, if I take the integral, closed loop integral over this curve, any curve. Okay, it could be a curve that looks like this. Okay, let's say you call it as C3, then in that case integration over C3, okay, this will also be 0. We know that this will be 0. This is 100%, we are sure about this, but this one we are not sure. Okay, this one there is doubtful. Okay, we are not really sure about this. Okay, so you can prove the Cauchy's integral theorem very easily. You can prove. We use something called as a Green's theorem. Okay, something called as a Green's theorem on a plane. Okay, so let me just tell you what the Green's theorem is. First, let me put this on the slide. Let me clear this. Okay. We use something called as a Green's theorem. This Green's theorem is probably something that you would have done in your course on vector analysis. Okay. So suppose I have a closed bounded region in a xy plane. Okay. Let's say something like this. I'll just highlight the important part. I have let R. What is this R? R is a closed bounded region. R is a closed bounded region. This result, Green's theorem, like I said, it comes from your vector analysis. Okay, it comes from a vector analysis. Green's theorem on a plane. So plane means we have here x-axis and y-axis. Okay. Remember, we are not talking about the complex plane. Okay, this is any plane. Okay, this is any plane, x and y. Okay, any plane. So I have some plane. Then R is a closed bounded region. Closed bounded region. What do you mean by closed bounded region? So we have a region which is something like this. Okay, so this is one region which lies in the xy plane. So this is that region. Let me use some other color. So this is one region which is closed and bounded. So this region we call it as R. Okay, this region is R. Okay, so R is a closed bounded region in the xy plane, and then this R has got a boundary. This R has got a boundary. The boundary of R is C. Okay, now this C, it says that C could consist of finitely many smooth curves. Finitely many smooth curves. What do you understand by this? Can anyone tell me? Whose boundary C consists of finitely many smooth curves? Can anyone tell me what this means? Finitely smooth curves, what does that mean? finitely smooth curves. Can anyone tell me what it means? You see, in this example that I have drawn this boundary. I have assumed the boundary to be smooth, right? I have assumed the boundary to be smooth. But whereas you could also have a boundary like this. Okay, we could also have talk about a boundary that looks like this. This is also allowed. This is not, this is this boundary. You look at the boundary here. This boundary C. This boundary, it is not made up of one single smooth curve, right? Here it is made up of one single smooth curve, but here this is one smooth curve. This is one smooth curve. Similarly, this is another smooth curve. This is another smooth curve. This is another smooth curve. Then this is another smooth curve, and this is one more smooth curve. So how many smooth curves we have? We have 5 smooth curves. 5 smooth curves coming together and forms a boundary, which we call as C. So that's the meaning of this. Finitely many smooth curves. So you need not have one single smooth boundary. It could be that boundary could be made up of many finitely smooth curves coming together and defining a boundary region. So that is also allowed. Okay. So we have R, which is a closed bounded region, and then we have its boundary, which is C. Okay, its boundary, which is C. So we have the boundary C, which consists of many, which could consist of many finitely smooth curves. Then suppose there are two functions f1 and f2. Suppose that now there are two functions f1 and f2, and these two functions are continuous. Okay, so there are two functions which are defined on this in this region. There is one function which we call as f1, and there is another function f2 which is also defined on the same region. Both of them are functions of x and y. Both of these are functions of x and y. Okay. Now, what are we considering? These functions are, they are continuous. First of all, we'll assume that these functions are continuous, and secondly, these functions also have partial continuous partial derivatives. So not only the functions are continuous, but the functions, they have continuous partial derivatives everywhere within this some domain is containing R. Okay. In some, maybe some superset of R in that region, everywhere these two functions, they are continuous, then they have continuous partial derivatives. If that is the case, then the Green's theorem says this. The Green's theorem says the integration of these two functions, over this boundary, if you integrate these two functions over this boundary, integration of these two functions of f1 dx plus f2 dy, okay, over this boundary, it is equal to the surface integral of the derivatives of these two functions within the region which is contained by this boundary. So the boundary is C. I want to integrate these two functions f1 dx, f2 dy. I want to integrate these two functions f1 with respect to x and f2 with respect to y over this boundary. Instead of integrating over this boundary, we could just take the partial derivatives of these two functions, partial derivative of f2 with respect to x, partial derivative of f1 with respect to y, and then the difference between these two partial derivatives, that is this quantity, we could just integrate this over this entire area. So this surface integral is equal to this line integral. Okay, so what it says is this is a line integral. This is a closed line integral. This is a closed line integral, and this one is a surface integral. This is a surface integral. So what the Green's theorem says is this line integral is equal to this surface integral. Okay, the proof of this is not required. We just need to use this result in trying to prove the Cauchy's integral theorem. Okay, is this clear to everyone? Has everybody understood?
Yes, sir.
Okay.
Yes, sir.
Now going back to this. Next slide. So this is the Green's theorem. Okay, this is the Green's theorem. All right. So now let us do this kind of a substitution. Okay, what we'll do is, remember, we are talking about analytic functions, right? We are saying that the function fz, we are assuming function fz. And what is function fz? U x comma y plus I v x comma y. Okay, so this is the analytic function. We say that this function is analytic. We say that this function is analytic. If this function is analytic, that means u and v, they are continuous, and u and v, they have continuous partial derivatives. We have already seen that. No. Now see, this u and v, they are also functions of x and y. No. And here, as per Green's theorem, what is this f1? F1 is a function of x and y, and f2, this is also a function of x and y, right? F1 and f2, both of them are functions of x and y. So if f1 can be any function of x and y, and f2 can be any function of x and y, I might as well set f1, I could make it equal to u, and f2 I could make it equal to v, and then I could just apply the Green's theorem. Not v, f2 I'll make it as equal to minus v. Okay, so f1 is u and f2 is minus v. I just use that, and when I do that, this is going to give us here f1 will be replaced with u, f1 we replace this with u, and f2 we replace this with minus v. Similarly here, f2 I replace it with minus v, and f1 we replace with u, and as a result, this is what you'll get. So you'll get u dx minus v dy, u dx minus v dy, the closed loop integral of u dx minus v dy, closed loop or integral over c. This must be equal to the surface integral of, so we have f2 is equal, is I have replaced it with minus v, so this is going to become minus dou v by dou x minus dou u by dou y into dx dy. Is this clear? So all I have done is I have just replaced f1 and f2 because the Green's theorem is applicable. The Green's theorem is applicable for any arbitrary functions f1 and f2. Any arbitrary functions of x and y, the Green's theorem is valid. Okay, because this Green's theorem, it comes from your vector calculus. It is valid for any arbitrary function f1 and f2. So I might as well replace f1 with u, and which is u. U is a real part of the analytic function f of z, and f2 I replace with minus v, where v is the imaginary part of the analytic function f of z. And when I do that, I get this expression, which we call as equation number 2. Is this clear to everyone?
Yes.
Is everybody
Yes,
clear
sir.
with this?
Sir.
Okay. So next what we do is we swap them now. Now what we'll do is this f1, okay, f1, I will make it equal to, instead of making f1 equal to u, now I'll make f1 equal to v, and f2 I'll make it equal to u. Same thing over here also. f1 is equal to v, and f2 I'll make it equal to u. And when I do that, I'll get v dx on the left hand side, v dx plus u dy, okay, closed loop integral of this, which is equal to the surface integration of dou v by dou x, dou u by dou x minus dou v by dou y. Okay, just making this substitution. So this is your equation number 2 and equation number 3. Okay, is this clear?
Sir.
Okay, so once this
Yes,
is
sir.
done, then yeah, once this is done, now next what we do is we will multiply to equation number 3. I will multiply I, okay, and then add it to equation number 2. So basically what I'll do is I'll multiply to this equation number 3. I will multiply this with I, okay, this entire equation. I multiply this with I, and I'll add this, whatever is the result, okay, I'll add it to equation number 2. Okay, multiply this entire equation with I and add it to equation number 2. So in that case, when we do that, what will happen is, so we have u dx minus v dy plus I v dx plus I u dy. That is what is going to be on the left hand side. And then here also we'll have I into dou u by dou x will get added here, and I minus I into dou v by dou y, which will get added over here. And when we do that, this is what we get. Okay, so we have left hand side u dx minus v dy plus I into, this is from the equation number 3 multiplied with I. Right hand side, this is the right hand side of equation number 2, and this is the right hand side of equation number 3 multiplied with I. So this is what we get. Okay, now just little bit of manipulation and rearrangement and manipulation. So what we have here is, on the left hand side, if you see, this is nothing but f of z dz. Do you agree? This is nothing but f of z dz. Can you see how? This is integration of f of z dz. Are you able to see how? If you're not able to see, we need to actually go back. to one of the previous results using this. Okay, we use this result, integration f of z. We already derived this, no, the definition of the line, complex line integral. This is f of z integration. So if you look at this, if you write down this equation and then you compare it with what we had got on the left hand side, they are one and the same. So these four integrals together will give us f of z. So let me just write this down here, this integral. So we have, integration over c f of z dz. This is equal to integration over c u dx minus integration over c v dy plus I into integration over c u dy plus I into integration over c v dx. So this is what we got. Okay, you can just compare. So we have u dx, this is u dx. Okay, so this is u dx, then minus v dy is over here, plus I into u dy, I into u dy is this, and plus I into v dx is this. So this entire thing is nothing but integration of f of z dz. Is this clear?
Yes, sir.
Okay.
Yes, sir.
So now we have here on the right hand side, we have these two, right? Now again, another rearrangement, what I did was, you have dou v by dou x, we have minus dou v by dou x, and dou u by dou y, I bring it on this side. So there is a dou v by dou x here. Where is it? No, sorry. This, what I did was, we used the Cauchy-Riemann conditions, okay, from here to here. We use the Cauchy-Riemann conditions. Okay, and what is the Cauchy-Riemann conditions? Dou u by dou x is equal to dou v by dou y. This is the first Cauchy-Riemann condition which we applied over here. Here, this dou u by dou x, this dou u by dou x is replaced with dou v by dou y. Fine, that was the first Cauchy-Riemann condition, because we have assumed that this f that we have here, we have assumed that this f is analytic. Okay, we assume that this f is analytic. If f is analytic, then that means f satisfies. If f is analytic, any analytic function will satisfy the CR conditions, right? So if f is analytic, it will satisfy the CR conditions. That means these two will be valid. This is valid. And the second one is dou u by dou y. Dou u by dou y is equal to minus dou v by dou x, which is here. Dou u by dou y, which is equal to minus dou v by dou x. So this is Cauchy-Riemann condition 1, and this is Cauchy-Riemann condition 2. We use this two here. Then because of this minus sign, this minus is going to become plus. Is this clear to everyone?
Yes, sir.
Once that is done, yeah, okay. Once that is done, then rest of it is very straightforward, because we see that these two are same. So these two will get cancelled and these two will get cancelled. Okay. So once these two gets cancelled, so this is integrand is 0, this one's integrand is 0. So as a result, on the right hand side, we'll have 0. Yeah, using Cauchy-Riemann conditions, we got this, and on the right hand side, we will have 0. So this is your Cauchy integral theorem. Okay, this is the, oops. This is the Cauchy integral theorem. Okay. Okay, let me clear this now. All right, so now Cauchy integral, another one application of Cauchy integral theorem is, it leads to the realization that when you're trying to, of course, the Cauchy integral theorem says it is the theorem is valid for a closed loop, no? But it also tells us about this simple any path, any need not be a closed path, it could be an open path. if I want to integrate over an open path, it tells us that the line integral is independent of the path. It only depends on the endpoints. Okay, so that is independence of path. This is what I mean. So suppose I'm having 2 points. Okay, suppose I'm having 2 points. Let's say this is one point. Okay, let's say this point is Z1. Another point I am having, and this point is Z2. And these 2 points, they lie in some region. Okay, suppose this is some region. This region we call it as D. And let's say this function f of z, the function f of z is analytic everywhere on this region D. So we assume that f of z is analytic everywhere on this region D. If it is analytic everywhere in this region D, so now I could simply think about, I could think of some closed path. Okay, I could think of some closed path like this. I could use some closed path. Let's say I have some closed path such that this closed path contains these 2 points. So we could think of a closed path C. Then the line integral as per the Cauchy integral theorem, the line integral of f of z dz as per the Cauchy integral theorem, this must be 0. So we use this idea to prove that if you want to integrate from from z1 to z2, if you want to integrate from here, we'll prove that very easily. The proof is very easy. So using this, we will prove that if you want to integrate from z1 to z2, so if you want to integrate from z1 to z2, it really does not matter which path you take. Okay, it really does not matter which path you take. It could be any complicated path. Okay, it could be any complicated path. So let's say this path is C1, this is C2, this is C3, this is C4. So long as the endpoints remain the same, the integration over C1 will be equal to the integration over C2, which will be equal to the integration over C3, which will be integration over C4. Okay, so the path does not matter so long as the endpoints remain the same. Okay, so the line integral of f is independent of the path in D. Okay, let me clear this. So this is path independence. So how do I prove this? The proof is very simple. So like I said, so we'll consider a region D. In this region D, we have some path. Okay, this is the path, and we have Z1 and Z2. Okay, so these are the 2 points. Okay, so suppose I have a closed path C. So this closed path C in a simply connected domain. And now what I do is, because these 2 points, Z1 and Z2, it lies on this closed path. So what happens is Z1 and Z2, they partition this curve into 2 segments. Okay, they divide this entire closed loop. They divide the entire closed loop into 2 segments, and those 2 segments are C1 and C2 star. This is C1 and this is C2 star. Okay, so it divides it into 2 different segments. Is that clear? And are we allowed to divide a path into segments? Yes, we are. We are allowed to divide a path into segments. How do you know that? Because of this finitely many smooth curves. Remember, the path could be made out of finitely many smooth curves. So no problem. I could as well divide the path into many segments. That is also fine. Okay, as long as it's a finitely, okay, the path is having a finite number of smooth curves. Okay, as long as that is there, then that's no problem. So I can this Z1 and Z2, it partitions the closed loop into 2 parts, C1 and C2 star. Then by if the function is analytic at all points, then by Cauchy's integral theorem, integration over C, integration over this entire closed path will be obviously 0, right? Integration of this over C will obviously be 0. Now because I have partitioned this C I have partitioned into 2 parts, C1 plus C2 star. That means the integration over C is equal to integration over C1 plus integration over C2 star. Now this is closed loop integral C. It will be equal to open integral over C1 and open integral over C2. This is a mistake, okay? This should not be closed integral, okay? This should not be closed integral. It should be a open integral. So this circle will not be there. Okay, by mistake I had put this circle. I will correct that, okay? So we have C1 integration over C1 and C2. Okay, this one is from the property, that property of partitioning of path. We had done this properties of the line integral. Okay, I think it's somewhere here in the very same set of slides. The properties of line integral, you see, partitioning of path. I've used this partitioning of path property. Okay, so I have partitioned the path into two parts, and the total integral over the entire path will be the sum of the integrals over the two partitions. Okay, then now what I can do is this one C2. Now you can see here C2 is from Z1 to Z2, right? You can see here this C2 star that we have, the C2 star, where does it go from? Its starting point is Z2. Its starting point is Z2, and from Z2 it goes to point Z1. It goes from Z2 to Z1. So now if I reverse this direction, instead of going from Z2 to Z1, let's say I go from Z1 to Z2. This path I'll call it as, let's say, C2. You're going from Z1 to Z2 instead. I'll call this path as C2. Now there is another property as the property of sense reversal. Okay, property of sense reversal, which again we had done earlier. The property of sense reversal. See, sense reversal. If you change the path, if you, instead of going one way, if you go the other way around, then this is going to lead to a minus sign. An additional minus sign will come into the picture. So this is known as the property of sense reversal. So here the same thing is happening. Instead of you're going from C2 star, okay, from C2 star was from Z2 to Z1. You are going from Z1 to Z2, the other way around. So this path I'll call it as C2. So according to the principle of sense reversal, integration over C2 star, if you reverse the direction, if you make it a C2, if you go in the other way around, then you'll have to include a minus sign. This is the property of sense reversal. Okay, and as a result of this property, this integral, when I replace this with C2, this plus is going to become minus. The plus becomes minus. Is this clear? So now right hand side there is a 0. We can always bring this on the other side. So it really does not matter. It really does not matter if you're trying to integrate from Z1 to Z2. It really does not matter. You could go this way, or you could go this way, or you could take some other path like this, because after all, this, if you reverse the direction, this will also form a closed path, and over that again the result, according to Cauchy integral theorem, the result will be 0. Or you could take some other path like this. So the path does not matter so long as the endpoints are the same. Okay, is this clear?
Yes.
Yes, sir.
Any questions? Any questions? Okay, so existence of the indefinite integral. So this one is a little bit involved. Okay, so we have a little bit of this derivation over here. So let me do one thing. This we'll do this in tomorrow's class. Okay, tomorrow's class, because this one will take a little bit of understanding. Okay, we are going to introduce some dummy variables and do this. So tomorrow's class we will do this. Is that clear? If you have any questions, you may ask me now. Okay, so we have some properties that we'll have to do, and tomorrow's class I'll start with this derivation, and then we'll do the other properties, and this will lead us to the Cauchy integral theorem. Then we can Cauchy integral formula. Then we'll be able to use this to actually solve some numerical problems. Okay, some applications we can do this. Okay, any questions do you have so far? Whatever we have done.
Excuse me, sir.
Yeah.
Sir, this property is same as the property of conservative force fields, I think.
Yes, in fact, very good question. Okay, conservative forces that you're talking about, I'm glad that it came to your mind. Conservative forces, actually, that's basically a potential problem, right? That's a potential problem.
Sir, potential problem, yes, sir.
And this potential problem, if you look at it in a more general way, the potential form, you could actually write it as a complex function problem. Okay, you could write
Yes,
it as a, you could map it to a complex function, solve that complex function, and then take the real part that is going to give you your conservation of energy that we're talking about. No, same thing you'll get central force field. All of this actually you can ultimately you could write this as a complex function problem only. Okay,
means sir,
very good.
like generally, like we don't represent gravitational electrostatic potential, like they are scalar potentials, right, sir?
Yes,
Means like the
but
vector, the
scalar,
magnetic
but
potentials that can be like, I was thinking about the magnetic potential that can be vectors, so can be represented as a complex function.
but that will not be a this one. That is not going to be conservative. Magnetic vector potential is not going to be conservative.
Okay, sir.
Scalar potential will be conservative.
Conservative,
Okay,
yes, sir. Yeah.
scalar potential, it has even though it's scalar, but it still depends on x and y. No, both of it depends on both the coordinates x, y, as well as z. Also, it depends on no. But
Yes,
vector
sir.
potential is not going to be conservative. So no, this you cannot apply in that case. Okay.
Okay,
Even
sir.
actually the scalar potential that you're talking about, no, even that also when you consider the electric field, we said electric field is a conservative field, but that is only in the static case. In the
Static case,
dynamic
yes, sir. Yeah.
in the dynamic case, the electric field will no longer be,
Conservative field, yeah.
conservative anymore. We will do this in detail next semester. We have a course on electrodynamics. I will be taking that course, so we will do that in more detail over there. Okay.
Okay, sir. Yes, sir.
All right. Any other questions? Okay, if there are no other questions, then I think we can stop here. Tomorrow's class, we will continue with this particular derivation. Okay. So let me just open your attendance sheet. So how many are present today? 14 of you are present. Okay. Okay, your attendance link is open. Please go to that link and provide your attendance and you can leave.
Thank you, sir.
Yeah.
Thank you, sir.
Yeah.
Sir,
Hmm.
sir, one thing,
Yeah, tell
like,
me.
yeah, sir, like in the potential problems of quantum mechanics, sir.
Huh.
So there we can take complex potential, right, sir?
If you are complex potential, which problem you're talking about?
Like, so not exactly. I'm not remembering the specific problem. I've seen some problem we are taking like this. So
No,
sir,
you
it
see,
is.
in
It is.
quantum, no, in quantum mechanics, you have to be particular about the problem, okay? Because
Okay,
it's
sir.
just if you're, let's say, for example, considering a potential, a scalar, the scalar potential, generally we consider potentials which depend only on position, okay, and do not change with time. And we assume the potentials to be, real functions only. Then it is going to give a wave function which will have a real and an imaginary part. If you take complex functions, the potentials to itself to be complex, I don't know any, I'm not able to find any real scenario where that will be applicable. So in that, because that is going to actually complicate your solution of the Schrodinger
Okay,
equation.
sir.
Hmm?
Okay, sir.
Hmm.
Like I said, like in any
So we
pure
have
state.
to,
Yeah, like pure state potential, like
Pure
we have
state
to
of
take all
that's
these.
what I'm asking. No, that's what I'm asking. Pure state of what? What exact problem do you are having in mind? That you have to be sure of first. Okay.
Okay, sir. Okay, sir. Okay, sir. I will just look in the problems, right? Remembering something
It's
I'm
better
reading
you
on.
just discuss that with your quantum mechanics teacher. Okay.
Okay, sir.
I don't because I don't want to intrude into some other subject. That's the thing. Okay.
So I thought, sir, you're teaching this point, so I just asked.
No, I'm not teaching quantum. No.
No, sir.
Yeah, I'm teaching you this
This is-
part, but then about quantum mechanics, what exactly kind of potentials that is there in your course and which you'll be using, that part I'm not really sure of. No, so it's better that you talk to your quantum mechanics teacher only about this.